It's really it's a place and a cache. So maybe stage, yeah, special space. Caching. Yeah. Wonderful. Our control management. Yeah, very good. So the instruction was the whole 15 and developed to from and the natural inside. So I'll give you the command that is right around 10 minutes. That means that so you have 12 minutes to present. And I'll give you a sign that 10 minutes are. It's 2 minutes per minute. You can go for 12 minutes. I can talk about it. Okay, but I'll give you a sign at it. So you can find the time, right? 10 minutes. I'll say 12 minutes. Oh, you will tell me. Yeah. Oh, I see. Okay. I understand. That's fine. Forward. Are you on? I'm taking the time. Getting back to the first one. You get to your specific? Yeah. Yeah. I think it's like the journey, so I'll give you 1 and 5 minutes left. But 5 minutes plus 3 for questions. Depends on what we get. Roughly how many people are expected? Is it better to wait for time after this session? Primary session. Yes, it's a really good. Okay. Always. Next time. We'll see. It's not good. We are from I come to Pareto or university. So that's why you don't look like just what are you thinking? Yes. So these what you think that this so count by that. After one. I see. And then our work actually become. And then first one. I always do this. Yeah. Yeah, I mean. Computing for system. Yeah, that's fine. I'm trying to call that. Now they have. What do you know? What single session? How that's single session. We do want to. It's a very good. Now people don't like question, but yeah. But very. Other people this kind of soup. During COVID, we was thinking, during COVID time, it's a very good support. But let's do one. Let's open up the tab. Also, we can delay it by 5 minutes. We can delay it by 5 minutes. Yeah, it should be fine.
Is there a way to do full screen?
And the keynote will be just ended.
Possibly.
So if you see a wave of people walking by, maybe we can give it a minute after that and then.
Pretty sunny outside.
Did you check the other speakers for the?
I hope I know we want to.
Anyone else giving a talk on the session? Even the speakers haven't got. Is anyone a speaker in this session? Anyone giving a talk on this session? Okay, one more speaker.
And the second.
Second speaker, third speaker, okay.
Third.
Okay. I'm the first speaker, so we have three speakers.
Yes, yes. So could the speaker be online? No, not on. No remote presentation, there is one before.
So overall 5 talks?
Right.
Okay, so we need one more speaker now.
Yep. Last call. Where's the other one? Where? Session. Right, I think
Okay.
we should get going. Thanks everyone for attending this systems 2 session on data exploration and optimization. So the general housekeeping is that you will get like 12 minutes to talk. I'll give you a warning when 5 minutes are left. And again, another warning if when 2 minutes are left. So without further ado, our first speaker is Lakshmi Subramanian from all the way from New York, and he's going to talk about MAML towards a faster web in geological units.
Okay, thank you very much.
So I'm going to describe my talk in one sentence. You all program web pages in a language called HTML. So we are introducing a new standard called MAML, which is Mobile App Markup Language, which essentially beats the pants out of various scripting frameworks, including the Google accelerated mobile web pages. And we can give you beautiful web pages without using any JavaScript. If you understood that, you understood my talk, okay? So the web is a mess, right? If you go to Facebook and you want to download your Facebook page, you're sometimes downloading 700 to 1,000 objects, but you have no idea why you're downloading. There's JavaScript, there's HTML, there's Python scripts, SQL scripts, shell scripts, whatnot, and so on, right? And if you look at the median number of JavaScripts in content requests per page, you would actually see that the distribution of JavaScripts is starting to look a lot higher than just your web page. So here's a funny story, right? I download Bootstrap to write my beautiful web page. But without my knowledge, I'm downloading the whole Bootstrap package with 7,000 Java functions, of which I use. Okay. So now there is an NPM package for everything, right? So the modern web page is really good. It's enormous amount of time to load, especially in developing countries when the bandwidth is much smaller. Now, not only is it a number of pages, you start opening a huge number of TCP connections which fight with each other. Half of them go into timeout and nothing loads, right? And somebody came up with a brilliant innovation called HTTP2, where the brilliant innovation was they reduced the number of TCP connections to a fixed number. They're like, you cannot open more than a fixed number of connections. Then what did people do? They open CNN1, CNN2, CNN3, CNN4. They open different websites with the same domain name. They open 6 connections per domain. So humans who want to make their web page faster do all sorts of crazy tricks just to make it a mess, okay? So given all this, I want to get to one very basic aspect. So when you download a page, you load a page, then somewhere deep inside it says, go download the JavaScript. And then that JavaScript says, go download the JavaScript, go download this other JavaScript, and the thing goes on in a hierarchical DOM structure. Okay? A web page is a rectangle. Something comes here, something comes here, something comes here, something comes here, something comes here. So if I know what is going to come in a page, and if I know what I need to fill in each box, it is just a paint job. So can I derive a flat structure of the final answer? So can I take a DOM-based structure and literally derive a flat structure as if it's a painting of a collection of rectangles? That's what we're trying to do in a mobile app markup language. So elements are modular, are absolutely positioned. There is no massive layout calculations, recalculations, and so on that you need to do, right? So what you really need to do is have some notion of absolute positioning with respect to some notion of relative position. So let me start with an example. You have a panda, right? You want to put a picture over there. So you put the WebP picture and you exactly say, you start at pixel number, 55, 100 and post a rectangle of size 50 by 50. And then you say, I am a panda. And that's another piece of text that goes below. So 2 lines of code, you take this image, put it over there, you take this text, you put it over there, and you're done. You don't need any fancy JavaScript to load a panda. Right? So you can actually do these kind of things with sort of dynamic positioning depending on the type of device, and you can figure out how to figure out the layout. And by the way, when you start your first JavaScript, you anyway share your entire life history. This is my browser, this is my this thing, this is my version, that is my version, this is my SSL version. You share your entire life history to that domain. Your entire cache history, your entire cookie history. So they know everything about you before loading your page. So you can actually figure out the right scaling factors from the original factors and the exact positioning when you want to render. Okay. Now, there are a whole bunch of JavaScript features. Oh, I want to do this, I want to track this, I want to track that, right? So we went through this entire laundry list, right? Okay, you want drop down menus? Okay, you can write a short script to do drop down menus. You want infinite scroll? We can do this. You want to have a video? Yes, we can do this. You want to do an image carousel? We can do it. You want to basically have specific things where elements appear after scrolling beyond a certain point? Yes, we can do it. You want countdown timers? You can do it. You want notification pops up? We can do it. And in the future, we can do 3 or 4 more things. Now, what we actually did was something very simple, right? There are useful JavaScript things and there are 20,000 useless JavaScript things. So we actually profiled a whole number of pages and we told that these are some of the most popular things. Why don't we write like a one-line command saying this is exactly what I want to do, this is the final answer. Right? So we create like a tinier version of JavaScript called mammal script, which doesn't have any fancy checking. So essentially the security properties are much stronger because you're not looking at the scope, you're not checking in a lot of other things. And essentially you can avoid a lot of web bloat using this, right? So you can actually say, down script and you can put your mammal script in there as to what you want to do. So the mammal script can also have event-based programming using listeners and triggers, right? For a click, for a change, for a key down, for a timer. You can support different types of triggers and vals similar to JavaScript, but the code is very structured, right? So on click button, you want to show image, you want to swap this, you want to do that, you can do all these kind of tricks, right? So we also did another fancy and funny thing, which is we built a mammal editor and a mammal translator. So you have an HTML page, we can give you a mammal page using a mammal translator. And we can also allow you to create your web page in an editor, which will give you the mammal output. So essentially we can do mammal to HTML, mammal script to JavaScript, so that you can actually check reverse compatibility of your pages and so on. So I don't want to get into details with respect to time. So one thing I want to actually say here is that if you compare mammal to the original page, we are getting dramatic reductions. Data savings over 90% of the web pages, with median saving of 1 megabyte when compared to and 2.4 megabytes when compared to the original for like a average page. Okay. So essentially we are able to and the AMP pages in terms of all the metrics across a variety of network conditions that you might see in developing countries, right? In terms of page load times per objects and across objects to render the page and so on, over 3G networks, 3G fast networks, LTE networks, and so on. Now, here is a really funny thing, right? Google introduced this project called AMP. And Google basically said, I will take your page and I'll give you an empty version of a page. I have 2 more minutes, right? Our pages are way smaller, look a lot more original, similar to the original page compared to the Google AMP page. And Google hired like 20, 30 engineers as part of their AMP team, put an IETF effort saying everybody in the world has to adopt AMP, and then shut down the whole AMP effort. Here we have a couple of grad students who built MAML, and we are able to show that MAML is able to do a lot better than Google AMP on even functional similarity, and also we have relatively limited impact of missing functionality, and some of it we can quite easily address in even future work. So there is something called as a visual similarity index on a 0 to 10 scale, and MAML outperforms by 3 points in this scale of 10, in where for a lot of pages, for a lot of functionalities, many people are saying it's very, very similar, almost similar, completely similar to the original page, right? And if you put a developer in the loop, you can push the similarity even further because we have a MAML editor. You can actually edit your page and you can actually go back and check whether you like it or not. So if you put a human in the loop, you can get much cleaner and complete web pages with the same amount of savings with basically closer to 100% functional similarity. So in summary, we basically have this flat layout based web specification language called mobile app markup language. And it was tested across a collection of 25 students based on user studies in this paper. Basically, it's able to handle many things. There are specific complex interactions that we are still working on. We're able to beat the pants out of AMP, and it loads very, very fast in very low networks. Today morning at 10:30, I gave a talk about my startup where we had actually used a version of this MAML in production in our Gaius framework, where Gaius is the name of the startup, for 2 million users across 2.5 years. And at that particular point, we were not even supporting JavaScript. But what has happened since then is we have added MAML script and handled a lot more JavaScript variations as part of this current version. We are hoping to make MAML into something much bigger, and potentially in the future, maybe people will not talk about HTML5 and maybe they'll talk about MAML. So with that, I'll stop and take questions. Thanks.
Thank you. Are there any questions to the speaker?
Yes.
Yes. I have one question about how do you determine the utility of the JavaScript again? Do you do dynamic testing of the file, or how do you determine which part of the JavaScript is necessary or not?
So we have published a whole series of papers before MAML, JS Cleaner, JS, some of them in www as well, where essentially what we've done is very detailed programmatic analysis of what is calling what, and is it actually touching something relevant with respect to the page. So in some sense, we're doing both code flow analysis as well as taking features of the JavaScript to learn some of these parameters. And because we had done a lot of that in prior work, we've been able to sort of implicitly use that as part of our MAML editor and translator to figure out what is useful and so on. Okay, thank you. Okay. You should look at some of our older work on JS Cleaner, where instead of MAML, we give you a simplified HTML version of the page. This is pushing it to an extreme level where we are trying to eliminate the JavaScript itself.
All right. Maybe one more question, because the idea is quite interesting. these JavaScripts are there for a reason. There is a huge internet economy behind that. How do you think that if you, adapt this, deploy this at scale, all this advertising and analytics, how will they take it?
So a lot of advertising, analytics, and so on are totally possible with MAML. Right? So we basically can handle many of the JavaScript event triggers and so on. Right? Including if you want to, if somebody clicks on this, store this as a database. The problem that is happening today is you write a JavaScript and then you put a wrapper around it, and somebody puts a wrapper around it, somebody puts a wrapper around it, somebody puts this whole thing with an NPM, I download the NPM, and after 6 calls, I finally figure out that one line of code that is actually going to do your analytics for you.
I see.
So when you just go to analytics, they say, oh, just add this one line JavaScript. But behind that scenes, it loads every damn thing, which makes no sense.
All right.
So,
Yep. Thank you very much. Let's
Okay.
thank the speaker.
Thank you.
Our speaker is Chi Sang from Shangguan Laboratory. He's going to talk about accelerating ubiquitous web browsing via schedule-driven space caching.
Okay. Hello, everyone. I am Qizhang from Zhongguan Laboratory, and it's my great honor to present our work, Space Accelerating Ubiquitous Web Browsing via Schedule-Driven Space Caching. And this is joint work from Zhongguan Laboratory and Tsinghua University from China. So let's get started. Geo-distributed web caching, utilizing numerous web cache servers around the world, has been crucial for reducing web access latency for years. And for example, Akamai is operating a vast global network of more than 4,200 sites, and including here in Sydney for all of us sitting here. And although alongside these established ground systems, we are also witnessing a new rise of low Earth orbit or LEO satellite networks. Starlink, a prominent example, now serves 4.6 million users from over 100 countries or regions, and especially from those underdeveloped regions, with a constellation of more than 7,000 satellites around the globe. So this interaction raises the core problem of our research. Is current distributed web caching ready for the future satellite internet? To answer this question, we start with a real-world measurement on web performance perceived by LSN users. So we measured from 76 Starlink probes hosted on Web Atlas problem, and with each of them, we ping the Alexa top 50 websites every 4 minutes and lasting for over 24 hours. We recorded the user to cache latencies or RTTs. So let's see the results. This figure shows the CDF of RTTs grouped by continents. So we observe that a large portion of LSN users are suffering from very high latency. Specifically, about 40,000 of global users and all users in Africa are experiencing an average RTT over 100 milliseconds, which is a very crucial perceivable latency threshold for the quality of web experience. And when you look at the RTT results grouped by different web ranks, you find that the high latency phenomenon is a common issue regardless of popularity ranks. So it's clear that the distributed web caching is not adequately ready. So to find out the reasons, we dissect the sources of these analyses with traceroute and other analysis. We found the following limitations, and firstly, a prominent example limitation is the limited cache coverage in the remote areas. The underlying cause is that the deployment of web cache servers has not kept pace with the rise of LSN. So let's see an example. Here is a user located in Benin, as the western part of Africa. And when it accesses google.com and amazon.com respectively, it's always assigned to a very far cache. For example, Johannesburg as a South Africa for Google and Ashburn in Virginia, US for Amazon. So when the access happens, although the request may arrive at a very nearby POP in Nigeria, also at the western part of Africa, it then has to travel very far, for example, over 7,000 kilometers to Google, or see the orange line via Paris, France, and then travels to Ashburn to Amazon. So resulting in an average RTT of 97.7 milliseconds and even over 200 milliseconds for Amazon. And the next limitation is we found is the routing detours between satellite and terrestrial ISPs, as cross-AS traffic is usually restricted to specific and sometimes inconvenient ground POPs and gateways. And here is an example. For a Starlink user located in Madagascar, an island east of Africa, when accessing Microsoft.com, it's sometimes assigned to a cache here in Sydney, Australia. And the route goes goes northwest via satellites and arriving at the Starlink POP in Frankfurt, Germany. And then it travels southeast via Singapore and all the way to Sydney. This results in cross-AS detours and ultimately user-to-cache latency up to 500 milliseconds. So to address these above limitations, and another limitation we didn't mention here, and please see the paper. Here is our approach. We propose to integrate web cache into LEO satellites, which is space caching, or space, the compound word of space and cache. And with cache servers integrated into LEO satellites, those contents can be directly served from the space. And this approach has some key benefits. Because the LEO satellites could cover the whole globe with this constellation of tens of thousands of satellites, it can provide global low latency access. And secondly, these LSNs usually could generally operate in one AS globally, so avoiding inter-ISP routing detours. And lastly, with direct service from space, it can help alleviate LSN last mile congestion by reducing traffic aggregation at the ground gateways and POPs. So although this idea seems promising, it comes with challenges, mostly resulting from the high dynamicity. So let's say these LEO satellites are moving at very high speed, about 7 kilometers per second relative to the Earth, and thus orbiting the Earth every about 90 minutes. And their ground trajectories are generally non-repeating due to the self-rotation of the Earth. And for example, in this figure, a satellite at the altitude of around 515 kilometers, it orbits along the orange line in one period and the blue line in the second period. So what's more, the global content consumption is ruled by geolocality, and meaning that different regions consume quite different content. And this is even true of adjacent regions. So these unique factors complicate the cache management on LEO satellites, bringing challenges. The first challenge is fast cooling. As the high satellite mobility lead to frequent service region switching. So when a satellite with a warm cache enters a new region, its cache effective status will become cool quickly because it doesn't contain the popular contents of the new region. And the second challenge is cache pollution, where these changing service regions result in dynamic request patterns and make the traditional replacement policies ineffective. So in the way that even after a while, the satellite serves the new region for a while, the content from previously served regions still remain in the cache, polluting it with irrelevant data. So it's quite similar to where we are now. So our conference dinner tonight is fully booked. And those attendees who won't really go there now are no longer irrelevant, and we have to fund them. Okay, our key insight to solve these challenges is leveraging areas and communication schedule information. So essentially, communication schedules of the RSNs define which entities, for example, we have satellite and user terminal and gateway here. It defines which entities should communicate with each other and when. So why does this exist? Let's see, with these schedules, the RSN operator has to make use of them to manage the frequent communication handovers between entities due to the high mobility, and to ensure seamlessly low-level communication connectivity for LSN users. So, and the LSN operators like Starlink typically pre-compute and pre-distribute these schedules to these entities. So with this, each entity and so each satellite knows when it will switch to serve the users of the new regions. Okay, with these pre-distributed schedules to each satellite, we design key mechanisms with using schedule-driven cache management on each LEO satellite. Firstly, schedule-driven prefetching. So we use schedule to prefetch the likely most popular content for incoming new regions before the switch actually happens. And with some specific mechanism designs in the paper, we make the prefetching perform just on time for each content and avoiding aggressive loading. The second mechanism is schedule-driven partitioning. We dynamically adjust cache space for different regions based on the schedule and avoiding inter-region pollution, and enabling rapid reallocation when a satellite abruptly exits the service area of a satellite. Okay, so let's move to the evaluation, and I have only 2 minutes left. To evaluate space, we implemented it and performed data-driven LSN simulation based on Starlink trajectories. And we generated requests based on realistic traffic patterns, and we also evaluated real web access performance using Mahi-Mahi emulation. And we compared the space with, firstly, ground-only caching and representing the current paradigm. And secondly, baseline space caching, which is schedule oblivious. And thirdly, Starfront recent work on satellite CDNs. Let's look at the heat results. The upper left figure shows that the space could significantly improve heat rate, especially with high request geodiversity. And the space is effective under various cache volumes and replacement policies. And the last space is resilient to temporal variability of requests, even though it utilizes these predicted schedules. And we also evaluate from the perspective of user experience. We found that space significantly reduces RTTs for global users, achieving, like in the leftmost figure, achieving a lower than 20 milliseconds average RTT for the top websites for all over the world users. And it also enables a page load time of less than 5 seconds on average for the top websites, reducing PLT by up to 7.4% compared to the SOTA Starfront. Okay, to conclude, in this paper, we identified 3 limitations of web caching. They are limited cache deployment, inter-ISP routing detours, and LSN link congestion. We proposed the space to integrate web cache into LEO satellites and use the special communication schedules of the LSN operators. And we show that through extensive evaluation that it could ensure consistently low latency globally. Okay, thank you. That's all, and I'm very happy to take any questions. Thank you.
Thank you. Are there any questions for the speaker? Yep.
Thank you for sharing your wonderful work. My question is, how do you conduct the pre-fitting?
How do you conduct
Pre-fitting?
prefetching?
Yeah. For example, if you predict the most possible candidates for the upcoming areas, which algorithm do you use?
Actually, we use prefetching itself is simple, right? The decision is when to prefetch what.
Yes.
And the algorithm, I have a backup for this, coincidentally. Yeah, so with schedule-driven prefetching, we have a list of the most popular contents of the incoming region. And for the left most popular content before entering the region R, the new region, we continuously assess at each moment, we assess the benefit to prefetch this content and the cost to prefetch it at this moment. And we compare this continuously and make the decisions.
Okay. So if you select a top key, such as top key with the most benefit and less cost.
Top K,
Top key having the most benefit and have a least cost, such as this.
Actually, to avoid aggressive loading, we do this for each content. The following the next most popular content,
Yeah.
and we compute the benefit and the cost to prefetch it at this moment. And if the cost is bigger, we do nothing and continue try again.
Oh, okay. I understand. Thank you.
Thanks.
Just one more question.
Thanks for the presentation. I'm a bit curious about if you consider how many storage space should a satellite should have each satellite have for the cache.
You mean like if you
The storage space?
Yeah, you mean when you're using in reality or?
Even in your simulation, if you have considered this aspect, because I think so. An infinite storage is unrealistic, but even at too small, I think that it will lead to a more aggressive fetching, right?
Okay, I will answer in the following aspects. So firstly, in our simulation, we use the cache size percentage to represent utilizing how much we can store in the cache as the percentage of the whole file catalog. And in reality, for those real satellites now, we already have like Exotech has launched the satellites storages from 1 terabytes to 40 terabytes on the real orbital satellites. Thank you.
I see. Thank you very much.
All right, let's thank the speaker again.
Thanks.
Our next speaker is Yudong Han from Peking University. The paper is G to GPU, Accelerating WebGL Applications via Dynamic API Translation to WebGPU.
Okay. Okay. So good afternoon, everyone. Thank you for coming to listening to my presentation. I'm Han Yudong from Peking University, and you can also call me Robin. Today, I'm honored to present our work, GL to GPU, accelerating WebGL applications via dynamic translation to Web GPU. Today, graphics rendering is crucial for enhancing the interactivity of modern web applications, powering experiences in gaming, data visualization, and VR. To support these use cases in the browser, developers rely on two main APIs, that is WebGL and Web GPU. Let's take a quick look at how they differ and why this difference matters. Released in 2011, WebGL has long become the widely used graphics API for the web. It is modeled after OpenGL ES and follows an imperative programming model, where developers issue step-by-step commands to configure the rendering pipeline by modifying a global state. This makes it relatively easy to learn and use. And Web GPU has been introduced in 2023 as the next generation web graphics API. It is designed to align with modern GPU architectures, following the programming model of Vulkan, Metal, and Direct3D 12. Unlike WebGL, Web GPU adopts a declarative programming model. Developers describe the entire low-level pipeline to using the descriptors and command buffers rather than modifying the state imperatively. This shift provides a fine-grained control that turns into a much better performance. To fulfill the improved performance, many developers have started to migrate their application from WebGL to Web GPU. However, this migration process introduced significant challenges. First, static translation requires extensive code modifications. And second, it is difficult to determine the full rendering pipeline state in the WebGL application at any given moment. And third, a naive one-to-one translation fails to take advantage of Web GPU's strengths. The translated application may suffer from the high overhead and even worse performance than before. These challenges primarily come from the fact that these two APIs follow a very different programming model. To release the potential of Web GPU to existing WebGL applications, we propose GL to GPU. It is a dynamic translator that converts a WebGL API calls to Web GPU in JS runtime. The design of GL to GPU is driven by three key goals. First, it must be seamless, just plug in and it works. And second, it must ensure the correctness. And finally, the translation must be efficient to deliver the real performance benefits of Web GPU. To achieve these goals, GL to GPU introduces three key components. First is JS-level prototype patching. And the second is state tracking with shader translation. And third, we have a set of runtime optimizations, including caching, batching, and bundling. Next, let me introduce the architecture of GL to GPU in more detail. On the left, we have a typical client-side WebGL application, which issues a set of WebGL API calls. We categorize these calls into four main types and process them separately. The first category is the state changes, such as enabling depth testing or setting blend functions. Second, shader setup, which compiles and links WebGL shaders. And third, uniform rise, where parameters like transformation matrices or lining data are uploaded to the GPU. And finally, vertex or texture uploads, which provide the actual geometry or images to render. The first step in GL to GPU is to intercept WebGL API calls from the running web application. To do this dynamically at runtime, we utilize a technique called JS prototype patching by replacing these prototype methods with our own wrappers. After intercepting WebGL API calls, the first task of GL to GPU is to emulate the WebGL global state rendering state, which is essential for generating correct Web GPU pipeline descriptors. To this end, as the app makes calls like gl.enable or gl.useProgram, GL to GPU dynamically update an in-memory emulated state. The next step is shader translation, converting the GLSL shaders into VXL. This process is not straightforward. The main reason behind that is VXL requires all global variables to be explicitly bound to the layout locations. In contrast, GLSL does not explicitly declare these locations. It depends on the variable names. To handle this mismatch, GL to GPU performs a shared variable merging step. So we extract the shared global variable names from the GLSL vertex and fragment shaders and merge them into a single set of bindings. Once the shared bindings are merged, we use existing shader translation tools such as Naga or Tint to convert the remaining shader bodies of the GLSL to valid VXLAN code. With these two models, all modifications to the WebGL rendering state are captured by our framework. However, directly constructing GPU descriptors would lead to a significant performance drop. Therefore, we introduce 3 optimizations to reduce the translation overhead. The first optimization mechanism is the fast retrieval of WebGPU rendering resources. To address this, we introduce a 2-level cache mechanism. The first layer of the cache maintains a transition graph, which is actually a DAG between these recorded WebGL global states. The second level cache is more straightforward. We directly cache the WebGPU resources corresponding to the state nodes of that DAG. And now let's talk about the second optimization, uniform batching. GLGPU leverage a feature of WebGPU called dynamic uniform to reduce the communication overhead, transferring uniform buffers from CPU to GPU. So to this end, we set a global uniform buffer stored on the CPU side to collect the uniform buffers from the various WebGL modifications. Every time a WebGL draw is issued, we append the corresponding uniform to the global buffer and record the offset. Once the global buffer is filled, we upload it to the GPU at once and clear it to prepare for the next batch. So let's talk about the last optimization, bundle management. Bundle is a feature brought by WebGPU to improve the reusability. You can visit the URL on this slide to see more details about that feature. To manage these bundles efficiently, GLGPU uses a trie structure. Each node in the trie represents a render bundle, while the edges represent the specific WebGPU operations like draw, set pipeline, or set vertex buffer. As each rendering operation is generated, GLGPU stores it in the trie. So this bundle can be reused if the same operation has been encountered before. Once the global uniform buffer from set 4 is filled, the WebGPU operation in the bundle can uniformly upload it to the GPU backend for rendering. So for write operations like WebGL vertex or texture buffer, we directly pass them into the WebGPU backend. So please refer to our paper for more details. So let's talk about the evaluation for GLT-GPU. First, GLT-GPU is implemented as a Node.js package and packed into a standalone JS file, making it easy to integrate into any applications. We utilize 3 popular benchmarks in the web ecosystem to test the performance, that is MotionMark, JS Gamebench, and Aquarium. We conducted experiments across a broad range of devices to ensure the comprehensive analysis. For the browser, we run our experiments in Google Chrome with full WebGPU support. Finally, for comparison, we use the native WebGL implementation as the baseline. So let's start by looking at the visual comparison. On the top line, we have the output from the traditional GLT-GPU application. On the bottom line is the same thing rendered using GLT-GPU. You will notice the difference is barely noticeable. And let's look at the numbers behind that consistency. We performed a pixel by pixel comparison over 100 consecutive frames using MSE, that is mean squared error. And GLT-GPU maintains extremely low MSE value across these 3 benchmarks, all below 0.006. The MSE between GLT-GPU and WebGL is actually lower than that MSE between 2 hardware platforms with the same WebGL backend. This strongly indicates that GLT-GPU maintains excellent visual consistency across translations. For the performance, to give you a more intuitive insight of GLT-GPU, I'd like to show you a short video demonstration comparing a WebGL application before and after translation. On the left, we have the WebGL, and on the right, we have GLT-GPU. So as you can see, the visual effect is actually smoother on the right side, right? Okay. So let us take a look at how it performs in rendering complexity increases. We increase the number of the rendered objects and measure the frame time. The frame time is the time to render a frame, and the lower is better. As you can see, GLT-GPU achieve up to 73.9 frame time reduction in MotionMark. And this result indicates that GLT-GPU demonstrates a pronounced improvement in end-to-end rendering performance. We also evaluate the adoption of GLT-GPU on a diverse set of devices. We observe the consistent improvements across all platforms. On average, GL to GPU reduced frame time by 45.05%. The result demonstrates the efficiency of GL to GPU across all these platforms. And to wrap up, we have present GL to GPU, a dynamic WebGL to WebGPU translation layer that runs in the JS runtime. We summarize our contributions as follows. First, we proposed a dynamic translation layer that converts WebGL to WebGPU in real time. Second, we introduced three optimization mechanisms designed tailored specifically for the programming model. Third, we comprehensively evaluated GL to GPU across a wide range of benchmarks, devices, and rendering complexities. Moreover, we are excited to push this further. We are exploring the predictive bundle management to further reduce the overhead of tracking and following the bundle management. We also aim to support real-world application or real-world engines. And we will also want to broaden the compatibility of GL to GPU to the WebGL conformance test suite, that is WebGL CTS for short. We hope GL to GPU can help the web ecosystem, especially in the graphics rendering field. And that is the end of the talk. Thanks for listening. You can see it through our demo or try it using on GitHub. I'm happy to take any questions now. Thank you.
Thank you. Do you have any questions for the speaker? Yep.
Well, it seems that your technology can also be applied to transform OpenGL to Vulkan. Have you ever considered that?
Yes, but we also considered this question before. That's a good question. And WebGPU itself has some features that WebGPU it is unique, like the bundles we just mentioned. So in fact, Vulkan doesn't provide these features designed especially for JavaScript. So our framework just use this feature of WebGPU to improve the final translation efficiency.
Do you mean you have finished that work in your previous research, transforming OpenGL to Vulkan? Did you just mean that?
I think it depends. It depends because you know that Vulkan has a range. It is difficult to intercept the Vulkan call, in fact.
Oh.
But I'm not sure if I answer right.
You leave it for the future works?
Yes.
Okay.
Yes.
Thank you. Are there any other questions? Yes.
Thanks. This is a great talk and excellent work. So could you elaborate a little bit on why you use try structure to handle the bundles? And you also mentioned that in your future work you are going to improve that part. So would you like to share a little bit about your insights about that?
Yeah, actually, this is a great question. We also considered this before, and the reason behind this try structure is that each node on the try tree represents a set of or sequence of WebGPU operations, like do this or do that before, do this and do that. And we can also broaden this data structure to like DAG or automation like machines like this before. And we to this end, try is the first try to fit these requirements. Yeah, and we can also change for another data structure for in the future. And that's a great question. Thank you.
Thank you.
All right. Looks like there are no other questions. Let's thank the speaker again.
Okay, thank you.
The next paper is Graph CSR, a space-time efficient sparse matrix representation for web scale graph processing. I believe it's a recording, so let's play the recording.
Role-Relational. a great honor to be here today. These are space transition sparse matrix representation for web scale graph processing. As you can see, this report is divided into four parts. First, use the backgrounds and data processing. Focuses on the third stage, especially how graph data is stored. In graph data storage, relationships between policies. However, real-world graphs
I don't think there is anyone to answer any of the questions. So let's go to the next paper. The next presenter is Juan Win Tran from University of Queensland. He's going to present the paper on-device content-based recommendation with single-shot embedding pruning, a cooperative game perspective.
Okay. This one. Can I try to use it? Yeah. Okay. I think it's this. Oh. Of course. The present button here. Oh. Okay. Okay. Hello, everyone. So today I'm gonna introduce about my work. Divide contents by recommendation with single shot embedding pruning, a cooperative game perspective. And first, let's wait me a minute. Wait. Okay. Okay. Sorry. So let's start with what it contains by recommendation. Move this somewhere. Can we move this part somehow? Sorry. Okay. So for contents by recommendation, we will have this field instead of the interaction messages compared to traditional collaborative filtering, and we will have some side information such as user gender, movie genre, or producer, and this field will have some feature in them like male, female, action, comedy, and this will be further converted into binary representation. Such as here X as 1 and 0, and all these like sparse categorical feature will into like a dense representation, a very large embedding table you can see here before feeding into the model head to reveal the actual output. What? Sorry. Yeah, okay. Yeah. So as you can see, compared to the computer vision and NLP work, recommender system will have a very large embedding table, and this will be the main bottleneck for recommendation content space. So in this work, we want to reduce this embedding table. And my currently recommender system, we want to deploy them into mobile device activities. However, most of the current lightweight recommender system, the one that's trying to compress the embedding table, focus on achieving a single parameter budget for training, which will be not affordable when you have multiple device settings. You will need to do it for every single device. Therefore, we want to do this fast. The way that we do it is that we will try to find a score for each embedding parameter, and we will just sort this score and store them somewhere in the disk or something. And we will try to remove the k lowest value from this score, remove the k lowest value in the embedding table according to this score with any incoming budgets. So the main question for our research is what is the attribution score free here? And the answer is it's a Shapley value. So next, we should do a Shapley value. This is the high level. You can see that for embedding table, we will try to calculate the Shapley value based on a given data set and get the Shapley value and prune based on the memory budget. So first, let's start with what is Shapley value. So it's a concept from game theory that we will try to assign the contribution of a player in a game. The exact definition is that for the symbol or layer here, we will try to find the average difference between having I and not having I for each set, and the average value here will be called supply value of layer I, as shown in this image figure. Yeah. However, as you can see, the way that we need to sample every possible subset, so the time complexity will be 2 to the power of n. Yeah, this is very, very time consuming, as you can already tell. Therefore, most of the reason they try to calculate this faster by using the Monte Carlo approximation. We can do this by sampling the random order player in the game, and we just calculate the average based on this. So this is the exact equation, exact algorithm, and you can see that the time complexity here will be the number of sample, the number of time, the number of player, and the value function v here. However, cooperative games are not ML model, so we need to provide a definition mapping between ML model and supply value game theory. So layer here mean that the embedding parameter and having subset S mean that we will assign 0 to the one that not in S, and the game V will be the average log difference between having I and not having, having set S and not having set S parameter. So the time complexity for the game here will depend on the dataset D, and the actual time complexity in number of sample, time N, time D. This is very, very large. So one of the recent work from Knowledge 2020, they propose the concept of local game. So what I have defined called local game, and they found that the supply value of this local game is actually the same, the global game supply value, so it's all average. Therefore, instead of trying to calculate the supply value of the global game, we can randomly sample X and I from this dataset T and just like sampling it. And this will be much smaller to compute because we only need to compute one sample instead of the whole dataset. And in practice, we will look through the whole dataset instead of like random sampling here. But this is for easy to understand. And the time complexity will become D time M. However, in virtual datasets, this is our smallest dataset. The number of layers is still more than 17 million. So it's not infeasible to compare for recommended model. So we ask, can we do better than the one from Knowledge 2020? And lucky for us, CTL model or ML model. As CTL model, we have this field and feature concept. So we actually found that we can group the feature into the same game called game of field. At the choosing each embedding parameter at the player in the whole local game, we only consider the group of player like this in the same field. So this is the definition, and this is the main finding. The above finding, we can reduce the number of layers from 17 million to 600 something, and make our computation like traceable and be applicable in real world. Next, we will introduce another component of our work. It's called cookbook. So this concept is very popular mostly in vector quantization. And so the question here that assign 0, this is a very magic number. And as you can see in recommender system, we need to model the interaction between different features mostly to dot product, some kind of element-wise product. And if we're assigning 0, the interaction will be totally turned off. And this make the performance very bad. Therefore, we try to further extend our work by introducing this field-aware cookbook. So with tree field, we will have a cookbook with a tree here and like tree grow monitor according with the tree here. And instead of assigning 0 like this, we will try to assign the same value. This, for example, this is the same group of player, so we assign 0.3 on this cookbook. So here how we actually calculate our cookbook. We will base on the weighted of every feature in a field. Yeah, like this is just the equation. Next, I will move on to the experiment. First, this is our method compared to other method. This method requires you to train the model again and again for each parameter budget. And as you can see, our method can comparable with them. Like Jack here mean that we will assign 0, and C here mean that we will assign a cookbook. So this is the current equation, current experiment result. Next, I also want to compare with attribution-based pruning or post-training quantization, like this PTQ here or magnitude pruning. And it still shows that cookbook generally outperform all these other single source. Then next we will generally have 0 come right next to it. This is our result on another backbone. And next, currently we use the whole training and validation dataset as the datasets we use to calculate our sample value. So we wonder what is the effect of the amount of datasets we use. So in this experiment, we only use the validation datasets. And yeah, as you can see, as we increase the dataset size, the performance increase. And only on datasets that the amount of data we use impact a lot our performance. This is because our dataset is like very sparse and it has a lot of categorical features, but it's very small datasets compared to Rito and KDD. Next, we want to understand what is the difference between cookbook and 0. So we find out that the cookbook, they actually can achieve better result because they can assign more budgets, like memory budget, to low fluency feature, as you can see here, compared to 0, where they need to model the high frequency feature. And this is because we use weighted average. So the information about high frequency feature is stored inside the cookbook. Therefore, it can have more memory budget for the low frequency feature. That's all for me. Thank you for listening and feel free to ask any question.
All right, thank you.
Yeah.
Are there any questions to the speaker? Yes.
Yeah. Yeah, maybe Michael will be better.
Thank you for the talk. One question regarding the codebook versus the 0. I'm asking, so to say, is there any complexity difference? Because like if you 0 out items, I can imagine that it's like faster in training or learning or something. And if you like have this codebook approach and you still use this value in some sense, do you have any insights on that, on the complexity difference between those two approaches?
So the time complexity in our is first, the cookbook is generally very small compared to the whole embedding table. For example, here you can see that the embedding table will be number of features times like hidden size, which was 16, so it's around 17 million, and the number of fields only like 39. So the overhead is very, very small compared to the whole picture. Like just 17 million compared to 600 something.
Okay, all right, thanks.
All right, maybe I'll ask one more question. So usually recommendation systems have to be dynamic. So every time, it's dynamic, right? You have to keep updating it. So, so every time, when there is an update in the data set, can you compare your method, because it involves all these Shapley calculations, is it still comparable with other methods if you want to make it dynamic and adaptive?
It's actually very hard because we need to calculate the Shapley value and store it. So when you try to update the model, you will actually need to compute the Shapley value again. Sadly, this is one of our limitation. Yes.
All right, thank you very much. Let's thank again the speaker.
Thank you for attending.
So I think that's it for Systems 2 session in www. Thanks very much for being here.
Thank you for.
Yeah, thank you. Nice. Yeah, thank you. So few people. I'm very nervous and then nobody can fuck.
嗯，你还得说完再走。对，这些设备我们说那个玩意儿能删吗？如果不想再放上，这个文件夹未来会用来干什么？还是以后就没什么用了？
应该是没什么用吧？你有删除
官
的权限吗？
吗？官方有让教吗？就是要
这个应该就是官方的链接。
啊，对，
对
官方的链接。
对对对，
好的吧？
你
哦，
有
好像可以
你能删吗？
删哎，不知道，所有人都可以删所有人。
不行，他可能没有设置权限，你能让这个
应该用不上哈。没事，也不关系。哎。